The goal is to generalize methods by which we solve equations. There's a quadratic formula, which I hope you all know by this point in time. There's a cubic formula, which I doubt many of you have ever seen. There's a formula for solving equations of degree 4. When I printed it on a single sheet of paper, it turned out to be so small I could not read it without a magnifying glass. Insane. There is no equation, no formula to solve equations of degree 5 or higher. And the reason for that is really, really complicated. But it comes down to trying to figure out how we solve equations in general. So, that means the idea needs to be pulled out of the realm just of numbers and variables. I need to make it, unfortunately, more abstract. The structure I'm going to work with is called a group. And that means a definition. I need a set and a binary operation. Yes, sir.
Are those angle brackets or parentheses?
I've written those angle brackets. You'll see them as lots of different things.
Okay.
But at the moment, they're angles. Technically, there are 4 properties required. Textbook only lists 3 because it assumes one of them. I hate assumptions. So, I'm going to list all 4. But the first one is property 0. I need a closed the set to be closed under the operation. Then I need the operation to be associative. I need there to be an identity, which I will call E for the moment. And then once I have an identity, I can say I need inverses. So a group is a set with an operation that obeys all of these properties. I have closure, associative behavior of the operation, I have an identity, and once I have an identity, every element has an inverse. This sounds insane. You've seen this all over the place. Consider the integers under operation, addition. Does this satisfy all 4 of my properties? If you think so, then we should actually go through and figure that out. Hey, that's how you nodding. How do I know it's closed?
Like in terms of what's closed under, I know that say you have the number plus the number if you switch stats the same thing, so we got that property.
But that's not one of those properties listed up there. You say, I only have to show these things. What you've just shown is an extra property not up there at the moment. So, closure. What's closure mean? Reese?
If you take, so in this case, if you take two integers and add them, you get another integer.
And is that true? Okay, so I can actually write that out for property 0. I started to write star instead of plus, but I know what the operation is, so I don't need to write star. Okay. Is addition associative? You're adding 3 numbers. Doesn't matter which pair you add first, the first 2 or the second 2.
When you say close, you kind of mean that like, you know it's gonna be an integer, it can't be anything other than that, or?
Right. I can't add 2 integers and get a fraction that's not also an integer, right? I can't add 2 integers and get I. Can't add 2 integers and get pi somehow. Or even a third. So I've got to be able to say, when I perform this operation, I stay within my group. This property, the associative property for numbers, is something I'm sure works from back in discrete math, from back in elementary school where I was first taught to add, right? They kept telling me it doesn't matter what order you add numbers, and you could add the first 2, and add the third one to it, you could add the second 2, and then add the first one to it. It works. I have waved my hands at this. We're going to do that a lot. Writing a formal proof for addition associativity is a pain in the ass. We didn't even do it in discrete. We said this is a property of the integers and ran with it. Identity. That's property 2. Do we have an identity?
You got 0. Yeah.
Consider the integer 0. Adding 0 to any integer leaves the same value. That works. Oh, I've written 0 as an identity in Z. I should write, there's a typo up there. Not a huge typo, there's a typo.
2 zeros, the identity in Z.
Because there can be at most 1. We showed that on Thursday. Property 3. Now that I have an identity, does every element have an additive inverse? So this is a universal. To prove it, I need to consider an element in my integers. What's the appropriate thing to add to that to get the identity? Negative A. And that means that every single element in my set has an inverse. Therefore, the set of integers with the operation of addition forms a group. I have to specify the operation because there are multiple things we can do in the set of integers, right? I could do all sorts of other things in integers, and I could get things that are groups and things that aren't. If I change that operation to multiplication, would it still be a group?
It's not, because it doesn't satisfy the third condition, because you'd have to have like a fraction, not the identity.
Now, in order to do that, I have to know what that identity is, right? So I have to go through them in this order. Multiplying integers gives me integers. That's closed. Integer multiplication is associate. A times B times C. Doesn't matter whether I multiply A and B first or B and C first, it still works the same. There's an identity. The identity is 1. But every element doesn't have an inverse. In the set, 1/2 is a perfectly valid number. It's not an integer. So 2 doesn't have a multiplicative inverse. If I try and solve that, the resulting solution is not an integer. Now, that doesn't mean I can't make other sets. And operations go together perfectly well. I can use multiplication, I can use addition. It depends on what I choose. Let's consider these 4 complex numbers. 1, I, -1, and -I. Is this a group? It might not be obvious at first. I have to remember some complex numbers work, right? I is the square root of -1. So -I is the other, the negative square root of -1. I times I gives me -1. Negative I times negative I. Positive I squared, that's -1, that's in there. 1 times I, that's in there. -1 times I, that's in there. -1 times negative, this is closed. If you wanted to, you could actually write a little table, multiplication table, for these 4 numbers, right? You could make a chart. Like the operation table we talked about on Thursday, I could say, under the operation of multiplication, do all 16 of these and tell me what you get. If you only get elements from U4, then this is closed. Lo and behold, I do only get elements from U4. So I can now say, 0. U4 is closed under multiplication. If you multiply complex numbers, you stay complex numbers, you multiply these complex numbers, you stay in these sets. Is this associative? Now here's the problem. If I really want to be pedantic about it, I have to take all possible groups of 3 and do 2 multiplications for each one. That's 128 multiplications. I'll be here a while. But it works. Trust me? We could do 7 or 8 of them. I don't think you want to. But all you have to do is pick some and say, oh, 1 times I times negative 1. If I do it 1 times I and then I times negative 1, that's negative I. If I do negative 1 times I, that's negative I times 1. That's also negative I. It works regardless of which 2 I do first. Do I have an identity? Is there a number I multiply by that doesn't change stuff in this set? It would be 1 again. And I can see 1 times 1, 1 times I, 1 times negative 1, 1 times negative I, and in the other order, I times 1, negative 1 times 1, and negative I times 1. Does every element have an inverse? Is there something I multiply each one by, and I get 1 as a result? I should be able to list them, right? Only 4 elements. And we've been using a prime. Again, I stole that notation from the book, but what times 1 gives me 1? Well, that's easy. What times I gives me 1? Negative I. What times negative 1 gives me 1? And then what times negative I? So U4, under the operation of multiplication, is a group. I promise there's a reason for this group being named U4. I didn't pull it out of my ass. I did really give this a name that I think will be helpful moving forward. There are a lot of groups we use often. If we know we're using the same group in the same operation in multiple places, we might actually drop the operation. Just talk about the additive group of integers as the group of integers. And then from there on, say I'm going to use addition. I might talk about the multiplicative group U4 and then never mention that it's multiplication ever again. It's assumed. Oh, in U4 we do this. For now, I want to write all the operations so we keep our straight. Eventually, we'll get to the point where I just say, oh, group S3, and we'll all know what operation is supposed to go with that kind of group, so we won't have to write that. Questions? Hey, you said when we were talking about integers, it didn't matter what order we did our operation in, right? In U4, does it matter what order we do our operation in? Because I look at this table and I see a property that we mentioned on Thursday. This operation is strictly term.
Oh, I was gonna say, isn't it something with diagonals?
It is something with a diagonal. What was the term we used on Thursday to describe that? Commutative. A star B being the same as B star A. And in the table, it's folding across the diagonal. The stuff above the diagonal that goes from upper left to lower right. Stuff above, if I fold it over, should match exactly the stuff below.
An operation be associative but not commutative?
Absolutely. Matter of fact, we'll see several of them. The guy who described groups as being commutative or not commutative actually wants to reserve the word commutative for things that have more than one operation. So we're going to use that word differently. But he was so prominent in group theory that they decided to give his name to a group whose operation is commutative. A group is abelian if star is commutative on G. So an abelian group has a commutative operation. Both U4 and the integers under addition are abelian. I write that with a capital A. Sometimes it will become a lowercase a if I'm not paying attention. Some textbooks switch back and forth. But Niels Heinrich Abel is who this is named after. So, as we've seen, the integers under addition, the real numbers under addition, the rational numbers under addition, the complex numbers under addition. Addition makes life pretty straightforward, are all abelian groups. If I switch to multiplication, I lose some things. All of these are abelian groups too. What's the plus mean?
All positive numbers.
And the star?
Non-zero.
Non-zero. So positive numbers under multiplication, positive real numbers, is closed, associative, has an identity, 1, and every positive real number has a positive real multiplicative inverse. If I switch to non-zero, again, I've thrown out the one that screws up multiplying, right? Everything gets an inverse. The identity for all of those is 1. They're all abelian. Let's define the set of functions whose domain is real and whose codomain is real. under addition, that's an abelian group. Matrices of a particular size with real entries, that's an abelian group. Under addition. What about under multiplication? Either of those.
One on the left isn't, because you can't take 0 times anything to get 1.
And if I think about the functions that are real to real, right? Functions whose domain is all real numbers, I want the identity being 1, right? Multiplication, have the 0 function and stuff. Not even that, I have lots of functions that I can't take inverses of, right? X. Because if I take 1 over x, the domain is no longer in all real numbers, right? We can't have no 0 in the bottom. Uh-oh, my inverse is not in the same set. Matrix multiplication. First of all, I have to make sure that I'm dealing with matrices that can be multiplied, right? We won't even get closure. A 2 by 3 and another 2 by 3, you can't do matrix multiplication there. Those of you that are in linear right now, you will see this. It may not be familiar. Those who already took linear or have seen matrix multiplication, we did this much of it in discrete. We'll do some more of it here. Matrix multiplication isn't even closed. So I'm kind of screwed there, unless I change my set. When we're dealing with square matrices, we tend to get rid of the double subscript because we only need one, right? They're the same size, rows and columns. So if I have n by n matrices, is that a group under multiplication? Fix my multiplication issue, it's closed. It's associative. Is there an identity matrix? Absolutely. Does every square matrix have an inverse? No. One of my favorite examples of a non-invertible matrix is a matrix that contains 1, 1. Otherwise, we'll pick up on the mic. That matrix has no inverse. A matrix of all zeros has no inverse. Well, however, if I switch to only the matrices that are invertible, that's a smaller set, then this does work. The set GLNR, general linear, N is the size of the matrix, R stands for real entries. Again, I've taken care of each problem as we go along. In order for me to make closure, or even have the operation be well defined, I had to make sure that my matrices, no matter which two I pick, would always work. That's why I made them square. Then I get associativity, then I get identity. Now I'm saying only look at the ones that have inverses. That's a group. And Reese, this is exactly the example. Here is a perfect operation that is associative and is not commutative. When you do matrix multiplication in linear, that's one of the first things we find out is broken. So here's a perfectly well-defined operation. It works. It's got inverses, but it doesn't have commutativity. The order in which you do matrix multiplication is fundamental and matters a lot. You'll also hear this, instead of being called the general linear group, this way. You'll also see this written as GL of Rn. Which relates it to linear transformations. Transformations like we did in Calc 3 at the very end, where we talked about the Jacobian transformation, all that fun stuff. Transformations here. Linear transformations make a group. And the general linear group is the transformations in Rn. Questions? If you're looking at me and going, I've never seen matrix multiplication before, come to office hours this afternoon, I'll go through a whole bunch of them with you. But you've seen cross products, right? Product of two vectors is another vector. A times B, B times A are negative to one another. So even though it's associative, it's not commutative. I can change the operation to be anything I want. Matrix multiplication is a complicated operation. Regular multiplication is an easy operation. I can make up and call that an operation, as long as it's well defined and has unique outputs to inputs. Here is a brand new operation. On, what's that? What's Q star? Careful.
Non-zero.
Non-zero. If it was a plus, then it would be non-negative. This is non-zero. The star of A and B is 80 over 2. Is this a group? 4 questions. Here's another equation. Start at the top, property 0. If you star 2 non-zero rational numbers, is the result non-zero and rational? How do I know that that last thing, 80 over 2, is rational? Well, when you multiply fractions, you get another number that's a fraction. When you divide by 2, you put a 2 on the bottom of your fraction. That's all still a fraction. So it's definitely rational. Why do I know it's not 0?
Is that to be multiplied by 0?
Aha! Neither A nor B are 0, so their product can't be 0. Perfect. That makes this an element of Q star. So it is closed. I'll write this properly in a moment. Q star is closed under my operation star. Is star associative? Now you might think, well, of course it is. It's a modification of multiplication.
Question, so like, when you say this would be associative, would it be like A divided by 2 times B is still rational? Like that's how you'd set it up? Or
What's associative mean? Go back to the very definition of associative.
if you have like 3 terms, like A times B in parentheses times C is the same as.
So let's do that, and then let's do that. And we'll see if we get the same thing. Because that's exactly what I need to do, Noah, is I need to make sure that those are not just in the set, but that they're actually equal to each other. And I don't know what to start with. But, so up here in the corner, I'm going to write let A, B, C, the elements of Q star. So those are 3 things from my set. I now do A star B. Then I star that with C. So A star B is AB over 2. Star that with C. What do we get? Yes, but I need to know what rational number.
0.
That's not sufficient. I need to know exactly what this answer is.
AB over 2 times C over 2.
Let's simplify that fraction, right? The top will be ABC over 2. It's over another 2, so that'll be ABC over 4.
Where do you get that 2 on the bottom?
By the very definition of star, thing 1 star thing 2, multiply the 2 and then divide by 2.
Sorry.
Our definition when we started for star, take the 2 things, multiply them and divide by 2. Take the 2 things, multiply them and divide by 2.
So
Now do it in the other order. What if you do BC first?
A star BC over 2.
Okay. And then when I do the star there, I get A, BC over 2 over 2. On the top, I have ABC over 2. Then it's over 2 again. Divide by 2 twice, that's dividing by 4. Those match. Two down, 2 to go. What's the third one?
Does it have an identity?
I need an identity. What do I star by? Star by, not multiply by, star by. To get the same thing back. What's that mean?
Root 2b over, or 2 over AB. Wait, no.
I'm just multiplying by A. So I want to know what this E is.
Root 2.
Aha! Because this over here is AE over 2, and I want that to be equal to A. So E over 2 should be equal to 1, and that means that E should be 2. In this in this equation setup, I had A star E. Identity has to work on both sides. So let's see if E equals 2 works in the other order. 2 star A. What's that? Right. Now here's a really interesting setup. Because of the way we changed our operation, we changed what behaves as our identity. What's the fourth one? Inverse. So now I want A star something to give me E. That's why I need to do the identity first. I need to know what it is before I can go on and do inverses. Wait, we know what E is. E is 2. Great. I need to know how to solve A star question mark equals 2. What's the right thing to put here?
1 over A.
Okay, if I try 1 over A, then I'm going to get A star 1 over A. Well, that's A 1 over A over 2. That's 1/2. That's not right. 1 over A doesn't work.
4 over A.
Aha. Now, the other thing I could do is I could actually go through the process of looking at A star question mark as A question mark over 2, and I want that to equal 2, and then A question mark equals 4, so question mark equals 4 over A. Why do I know that that makes sense? Now, makes sense here is a really difficult thing because you look at this one, this doesn't make no sense at all, man. Why do I know that that question mark term, that inverse, is well defined?
Because that is our identity.
That makes it an inverse. But why do I know it's going to be in my set?
Because A is in the set.
And that makes A
Rational, non-zero rational number.
non-zero, which means I'm allowed to divide by it. So not only do I have an identity that's not what we expect it to be, I have an inverse that's not what we expect it to be, but it still is a member of my set. And therefore, this is a group. But wait, there's more. Is it abelian? What's that? Why, Jalen?
So if the question mark comes for star A, we should get the same answer.
Yes, but that only shows it to be true for the inverse. Abelian is now about everything in the group. What's it mean to be abelian? I can't hear you.
So we did B times A.
Do I get the same thing for B times A that I get for A times B? Are those the same?
Yeah.
Presto, it's abelian. Now, technically, I could have determined that this operation was commutative way back at step 0 or step 1. I didn't have to show that we had identities. I didn't have to show that we had inverses to know it was commutative. That wouldn't tell me it was an abelian group until I showed all 4 properties were true and the operation was commutative. But back up here where I did the identity, I showed the identity first on the right and then second on the left. If before that I had shown that star was commutative, I would have only had to do one of those. Because having done it on the left, it's automatically going to work on the right, or vice versa. I can't make that assumption. Down here where I did inverses, Jalen, you are exactly right. I only did one side. I really should have done question mark star A and showed that that worked out to be 2 as well. Having this now, I don't have to.
So if you can determine if it's abelian, you don't have to worry about, because it's already.
If I know I can flip A and B, then I can flip A and E, I can flip A and A inverse. So if I know I can flip, I then only have to do one side. So technically, this should be up there with the thing about inverses to show me that I actually have that flippability. I'm being rather loose about that at this point because I think it's more important to say, hey, this worked out to be a group. Then I showed it was abelian. More questions?
Would you want us to show it like that consistently? Or
I would appreciate it unless you've shown that your operation is commutative, that you show both sides. But again, depends on what the question asks. If you just ask, is this a group? Then don't worry about abelian at all. Or choose to worry about abelian and then only do half of number 3 and 4. Sorry, 2 and 3. Okay. If I don't know whether or not a group is abelian, then things can be different when I'm multiplying either order, which means I have to be careful about the order in which I write equations, the order in which I write expressions. X, Y, and YX could be different. So I can't combine quote-unquote like terms unless I'm in an abelian group where I know they're alike. Otherwise, they're not like terms. X, Y, and YX are not the same. But regardless of whether I have a group that's abelian or not, you still have some nice rules. canceling. We do this in algebra all the time. We cancel out 2's on both sides. Oh, what did I do? I divided, right? But my operation is star. Star isn't division. Star isn't multiplication. Star is weird. As we saw in our previous example, star could be really weird. I claim we can still cancel. We can cancel the A's on the left. We can cancel the B's on the right. So I have left cancellation and right cancellation. However, I wrote the word theorem up there. Theorem requires short. Promise. This is actually a very direct proof. So how do I prove this? Well, there are two versions of cancellation here. That means there should be two proofs. Turns out they're almost identical. So do you want to do left or right? Okay, that's this one, canceling the A on the left. Suppose all three of these things are in my set, and I have A star B equals A star C. What's property 3? I'm sorry. Definition, what's the group property to number 3? Every element has an inverse. That means there's an A inverse. Where E is my identity. So, if I have this equation, then I can put, oh, wait a second, I gotta be careful here. Not only is A star A prime equal to E, so is A prime star A. Gotta be careful with my order, yes? I'm gonna put an A prime on the left side of both of these pieces. I started to say multiply, but it isn't, it's star. So I'm going to star by A prime on the left. A prime star A star B is equal to A prime star A star C. And since I did it on the left, the two terms that were already there are considered a single object. My parentheses are there. What do we do now?
This is associated, we can make it A prime star A on both sides. That'll be in the parentheses.
Now what's inside the parentheses? So I use property 3, there is an inverse. I use property 1, my group is associative. What do I do now?
Since E is the identity, you just give B equals C.
Because that's the definition of the identity, which is where I wanted to end up in the first place. I wanted to show that if I had A star B equals A star C, then B was equal to C. A star B equals A star C, so B equals C. That's half the proof, because that's the left. What's the right? And then instead of doing B prime on the left, I would do B prime on the right. Everything else would be exactly the same. I move the parentheses, I turn the BB prime into an E, and that gives me A equals C. If my group is abelian, then that's both of them, right? Because A star B is the same as B star A. Canceling on the left and the same as canceling on the right. So that means in the universe of matrices, where I know I have a non-abelian group, I get lefts and rights that behave differently unless I can prove somehow that they're the same. Here again, I state it as a theorem. Which means I should be able to prove it. But if you're trying to solve this equation, how do I get rid of the A on the left-hand side with no A on the right-hand side?
What we find?
Go ahead, Jalen.
Would you find the inverse?
And then I multiply by the inverse. So X is equal to A prime star B. I multiply on the left. So I have a left inverse. How do I do Y star A?
The same with y. It's all with
I'm solving for Y, so I got to multiply
by a or b over a.
I don't have over.
Oh,
I
that's
have
right.
to use the inverse.
That's right.
And it'll be on the right instead of on the left because that's where we are. So X is A prime star B, Y is B star A prime, where A prime is the inverse of A. If my group is abelian, those will be the same, won't they? A, B, and B, A are the same when my group is abelian. That would be the same solution if this group were abelian, but they might not be. Didn't say anything about abelian in the theorem, did I? I did say the word unique. I'm back to discrete, chapter 1, section 8. Existence and uniqueness are proved separately. Now that I know I have a solution, how do I show it's the only one?
Sure, that's 1 to 1.
That sounds really complicated, showing star as 1 to 1. And I don't know that that's going to be easy. But I can cheat and use what we just proved the theorem before. Using a proof by contradiction. Suppose not. Then A star x1 is equal to B and A star x2 is equal to B. Right? Suppose I had two different solutions. Well, if they're both equal to b, then they're both equal to each other. Hey, wait a second. What did the theorem before this say? So they're not different, they're really the same, and that means the solution is unique. And if I can do it for x, I can do it for y exactly the same way. Hey, wait a minute. We already showed that there's only one identity, right? But this cancellation idea means that I can also show there's only one possible inverse. We already know that the identity thing is unique. So how would I go about showing that an inverse is unique?
It's not.
Exactly the way I did here. One sentence proofs, I like one sentence proofs. Those are easy. This gives rise to an amazingly nice corollary. And that's how you do the inverse of a product. How do you do the inverse of a product? I take the inverse of each one, but I reverse the order. Why? Because A star B star B prime star A prime equals I have to rearrange my parentheses, right? Associativity. So I take the B and the B prime and do those first. That becomes an E. It goes away. Then I have A star A prime. It goes away. Since an inverse must be unique, this is the one that works. So I can go away from saying an inverse or an identity. It's the in both cases. There's an inverse, only one. In some books, you'll see other algebraic structures. I had 4 different properties that made up a group, right? So what if I get rid of some of them? If I were to say, what if I only want associativity? I don't necessarily need inverses. I don't necessarily need identities. Well, then that's called a semigroup. If I stick back in the identity, that's called a monoid. And you'll see different places where having inverses is more useful or less useful. We're not going to cover semigroups. We're not going to cover monoids. You'll see them intermittently mentioned in other papers and in other sources. I am much happier to say that the group is the most basic structure we're going to deal with. Questions? Here are two groups. I claim fundamentally these are the same thing. I would like to show, to prove, to demonstrate to you that these two sets with their respective operations behave exactly the same. Now, I suppose I should write something particular down here. I'm going to write a 2. I run back to discrete. What is that plus with a sub 2 on it? That's addition mod 2. So let me think about the way this operation works. What's 0 plus 0? Good. 0 plus 1? 1 plus 0. 1 plus 1. Mod 2. 2 mod 2. By 2 by 2 and tell me the remainder.
0.
Please notice, every element, this is perfectly associated, this is closed. Every element has an inverse. And the identity is 0, right? You add 0 to something, it doesn't change. I'm dealing with multiplication over there. Multiplication has an identity of 1, usually normal, regular, ordinary multiplication. So what happens in that table? What do you get when you fill it in?
1, then -1 to its right, and then -1, 1.
So here's a relationship. I'm going to define a function from one set to the other. F goes from the set 0, 1 to the set 1, -1. And I'm going to define that function as follows. F of 0 is 1. And f of 1 is -1. The things that happen in the table on the left are exactly the same as the things that happen in the table on the right, aren't they? Just relabeled. And that means structurally, these two sets with these operations are really identical. They're really the same shape. Isomorphism. Iso, same, morph, shape. When you use it as a verb, it means to change things. When you use it as a noun, it literally means shape. So an isomorphism means these two things are really the same shape under here. A group isomorphism must be a one-to-one and on-to function from G1 to G2. And it has to preserve the way the operation works. So, f of a star 1b has to be the same as f of a star 2 f of b. So the things that happen in the left group behave the same as the things that happen in the right group. This property is so important, we give it a name in and of itself. The homomorphism property, the similar shape property. And if we can find such a function, then our groups are isomorphic. They are the same. Please note, I made a table to describe my group because tables for groups are really, really nice. Notice back in my group tables, each element appears exactly once in each row and each column. And that means that I can look at some table and say that's a group or that isn't very quickly. With the exception of checking, associativity. If I have 3 elements, one of them is going to have to be my identity, right? Well, now you have a choice. Here, what thing can go here? There are really only 2 choices. It's either E or B. Well, if it's B, then I could put an E here and that would work. If it's E, then B has to go here and B would be in the same column twice. So this has to be B for this to be a group. And then these have to be A's. These have to be E's for this to be a group. And that means this has to be an A. If I have a group with 3 things in it, no matter what the labels are, this is its table. There is only one group of size 3. They're all isomorphic to that. And that's really powerful. And that's why I want isomorphisms. I want to be able to understand this. The 2 groups I gave you, that's a group of order 2. I claim there's only one possible group of order 2, no matter what you label it. It looks like that table we just saw. There's only one possible group of order 3. It must look like this. Whether that's 0, 1, and 2 under addition mod 3, or some set of multiplications, or something to do with triangles, is only one way to do a group with 3 things. Now that's powerful. More examples on Thursday. I will see you all then.
Did we start getting homework already, Professor?
I'm about to collect it.